Welcome to the deep dive. This one's crafted just for you based on all the fascinating sources you sent over.
Yeah, a great collection of notes and articles.
Absolutely. And today, we're getting into something that still kind of blows my mind, honestly. Time dilation.
It does feel a bit like science fiction, doesn't it? Even though it's, well, confirmed science.
Exactly. So our mission here is to really unpack what time dilation actually is,
Yeah.
based only on these sources you've provided. We'll look at, what causes it according to Einstein, clear up some common myths.
And look at where it actually shows up in the real world. It's crucial for some tech we use daily.
Right. Okay, so let's dive in. What's the basic idea? Time dilation. What is it fundamentally?
Well, at its core, it's pretty straightforward definition-wise anyway. It's just the difference in the amount of time that passes as measured by two different clocks.
Okay, a difference in elapsed time.
Yeah. And the sources are really clear on this. It's not just about perception, like time feeling different. It's a real physical difference, an actual change in how much time has gone by.
Got it. Not just in your head. And the sources pin this down to two main causes, right? Both stemming from Einstein's relativity theories.
Precisely. The first one comes from special relativity. It's about relative velocity, how fast you're moving compared to someone else.
Okay.
Basically, the faster you move through space, the slower time passes for you relative to a stationary or slower moving observer. Speed literally affects your clock.
So speed's one piece, and the other involves gravity. That's general relativity.
Exactly right. The second cause is gravity, or more accurately, a difference in gravitational potential. Time moves slower where gravity is stronger.
Stronger gravity means slower time. So closer to a big planet or star.
Yes, closer to a massive object, you're deeper in its gravitational well, and time flows more slowly for you compared to someone further out where gravity is weaker.
So time isn't this universal metronome ticking the same everywhere. It depends on where you are and how fast you're moving.
That's the absolute core concept, and like you said, it's not just theory, it's been measured.
Okay, let's dig into the gravity part first. General relativity. It sounds weird that gravity, which pulls stuff, also messes with time. How does that work?
Well, general relativity tells us that massive objects don't just pull things through space, they actually warp or curve the fabric of space-time itself. Think of space-time as this combined four-dimensional sheet, almost.
The trampoline analogy.
Yeah.
I saw that in the sources. A bowling ball on a trampoline making a dip.
Exactly, and that dip represents the curvature of space-time caused by mass. But the sources add a key point to that analogy.
Right. It's not that a marble rolling nearby is pulled down a hill by some extra force.
No, exactly. The marble is just following the curve of the sheet. The shape of space-time itself dictates the path.
Okay, so the curve dictates motion through space.
And through time, the deeper the curve, the stronger the gravity, the slower time itself proceeds in that region. Further away, where the curve is shallower, weaker gravity, time runs faster.
And this isn't just for, like, black holes, right? This happens here on Earth.
Absolutely. The effect is tiny in our everyday experience, but it's definitely measurable. The sources mention experiments detecting time differences over just a few millimeters of height difference.
Millimeters. Wow.
Yeah.
How much difference are we talking?
Something like a 100 quadrillionth of a second difference. Vanishingly small, but real.
Okay, so minuscule locally. But does it add up?
It does. The sources give great examples. Say you spend 30 years living right at sea level and someone else spends 30 years on top of Mount Everest.
Higher up, so weaker gravity.
Right. The person on Everest would actually age about 0.91 milliseconds more over those 30 years. Time runs slightly faster for them.
Okay, 0.91 milliseconds.
Yeah.
Still tiny, but measurable. What about going lower?
Good question. Compare sea level to the Dead Sea, which is below sea level. Slightly stronger gravity there.
So time should run slower.
Correct. Over 30 years, the person at the Dead Sea would be about 44 millionths of a second younger than the person at sea level.
Fascinating. And over Earth's entire history.
Scale it way up. Over 4.6 billion years, according to the sources, a clock kept at the top of Mount Everest would be roughly 39 hours ahead of an identical clock kept at sea level.
39 hours. Okay, that really puts it in perspective. Small effects accumulate massively over time.
Definitely. And there was that light clock analogy in the sources, too, to try and visualize why gravity slows time.
Ah, yes, the light bouncing between mirrors.
Yeah, each bounce is a tick. In stronger gravity, space-time is more curved. It's a bit simplified, but you can think of the light having to travel a slightly longer bent path between the mirrors because of that curvature.
And since the speed of light is always constant.
A longer path means each tick takes longer. So the clock in stronger gravity ticks slower. It helps visualize the link between the geometry of space-time and the rate of time.
That's a helpful picture.
Great.
Okay, so that's gravitational time dilation. What about the other side, velocity? Speed affecting time.
Right, velocity time dilation. This comes from special relativity, and it's a really fundamental postulate. The speed of light in a vacuum is constant for all observers.
Regardless of how fast the observer is moving.
Exactly. Always measured at roughly 300,000 kilometers per second, which sounds simple, but it has massive consequences.
Yeah, the sources mention Einstein's thought experiments, like being on a streetcar, moving at light speed away from a clock tower. The clock hands would just stop from his perspective.
Right, because the light carrying the image of the next tick can never catch up to him if he's also moving at light speed.
And this created a clash, didn't it? Between Newton's ideas of adding speeds and Maxwell's equations showing light speed was constant.
It did. If you're running towards a thrown ball, it comes at you faster. Newton's laws work for balls, but light doesn't work like that. Run towards a light beam, it still comes at you at the speed of light, not faster.
So how did Einstein solve that?
His revolutionary idea was that space and time aren't rigid, absolute things. They are flexible, relative. They stretch and contract depending on your motion.
To keep the speed of light constant for everyone?
Precisely. If the speed of light must be the same for you, whether you're standing still or flying in a rocket, then something else has to give. And that something else is time itself. For the math to work, time must pass slower for the person in the rocket relative to the person standing still.
Wow. Okay. And the lightning strike example helps illustrate this relativity of time, right?
Yeah, the classic one. 2 lightning bolts strike the ends of a train platform simultaneously for someone standing on the platform.
Okay, simultaneous for the platform observer.
But now imagine someone on a very fast train moving past the platform, say, towards where the front bolt struck, because they are moving towards the light from the front strike and away from the light from the rear strike.
And the light from both travels at the same speed relative to the train observer.
They must see the front strike happen before the rear strike. Events that are simultaneous in one frame of reference aren't necessarily simultaneous in another frame moving relative to the first. Time itself is relative to your motion.
Mind-bending stuff. No wonder there's so many myths about it. The sources listed a few we should probably debunk.
Good idea. Yeah, people get some strange ideas.
Like the first one. Time dilation only happens near black holes or, in really extreme sci-fi scenarios.
Right, that's a common one. And it's just not true based on the sources. Yes, the effects are huge near black holes, but it happens anywhere. There's gravity or relative motion. We just talked about Earth's gravity causing it, even Mount Everest versus sea level.
So it's happening right now, just imperceptibly.
Exactly. Which leads to the second myth. You can actually feel time dilation in your daily life.
Which you can't, because the effects are way too small at normal speeds and gravity.
Correct. You'd need to be moving at a significant fraction of the speed of light or be in an incredibly intense gravitational field for the difference to be noticeable to your senses or even biological processes on a short time scale.
Okay. Myth 3. Time dilation breaks the laws of physics.
That one's completely backward. It is a consequence of the laws of physics, specifically Einstein's relativity. It's baked into how the universe works according to our best-tested theories. It doesn't violate physics, it is physics.
Right. It's a prediction that's been confirmed. What about the time travel one? Does time dilation mean time travel is real?
This one needs nuance. Time dilation does make forward time travel theoretically possible.
How so?
If you traveled in a super fast spaceship, say near light speed, for what feels like a year to you when you return to Earth, many, many more years might have passed for everyone back home. You've effectively jumped into their future.
Okay, so travel to the future, relatively speaking.
Yes, but, and this is crucial, the physics of time dilation, as we understand it from relativity, gives us no mechanism for traveling backward in time. It's not a time machine in the H.G. Wells sense.
Got it. Forward, yes. Backward, no. Last myth. Time dilation affects clocks, but it doesn't affect people, like our aging.
Also false. Time dilation affects the rate of time itself in a given reference frame. That means all processes occurring within that frame slow down relative to an outside observer.
Including biological ones.
Yes. Your heartbeat, your metabolism, cell division, thought processes, everything would slow down from the perspective of the outside observer. The astronaut on that fast ship wouldn't just find their clock ran slow, they would have biologically aged less too.
It affects the whole reality within that frame. So where do we actually see this playing out beyond thought experiments? The sources mention concrete evidence and, crucially, applications.
Yeah, absolutely. The famous twin paradox is a direct consequence of velocity time dilation.
Where one twin travels fast and comes back younger.
Exactly. And while we can't do that experiment with people, we see the equivalent effect constantly in particle physics labs. Short-lived particles, when accelerated to near light speed, survive much longer than they should because their internal clocks slow down, just as relativity predicts.
And the atomic clock experiments.
Yes, the Hafele Keating experiment back in the 70s and more precise ones since. They flew atomic clocks on commercial jets around the world.
Yeah.
And the clocks on the planes did show tiny differences in elapsed time compared to identical clocks left on the ground, matching the predictions that accounted for both their speed, velocity effect, and their altitude, gravitational effect.
Okay, direct experimental proof. But the big one, the one you mentioned affecting us daily, is GPS.
GPS is the killer app for relativity, honestly. It simply would not work without accounting for time dilation.
Because the satellites have clocks, and those clocks are both moving fast and are in weaker gravity.
That's right. They're orbiting at about 14,000 kilometers per hour, which causes their clocks to run slower due to velocity time dilation by about 7 microseconds per day compared to ground clocks.
Okay, 7 microseconds slower due to speed.
But they're also about 20,000 kilometers up, where Earth's gravity is significantly weaker than on the surface. This causes their clocks to run faster due to gravitational time dilation.
Faster. How much faster?
About 45 microseconds per day faster.
Ah, okay. So you've got minus at 7 from speed and plus 45 from gravity.
Exactly. The net effect is that the satellite clocks actually gain about 38 microseconds on ground clocks every single day. 45/7 equals 38.
38 microseconds a day. That
Oh.
still sounds tiny. Does it really matter for finding my way to the shops?
It matters enormously. GPS works by measuring the tiny time differences for signals arriving from different satellites. Light travels about 300 meters in 1 microsecond. So a 38 microsecond error per day means your calculated position would drift by over 10 kilometers every day. 38 microseconds, 300 meters microsecond, 11,400 meters. The whole system would be useless within minutes if it didn't correct for relativity.
Wow. Okay, I had no idea it was that critical. So how do they fix it?
Engineers build the correction right in. Before the satellites even launch, their atomic clocks are designed to tick slightly slower than identical clocks on the ground.
Slower on purpose.
Yes, by precisely the amount needed to counteract the net relativistic effect they'll experience in orbit. So once they're up there, moving fast in weaker gravity, their clocks actually tick at the same rate as clocks on Earth's surface, or technically on the reference geoid.
That's clever. Pre-correcting them.
Yeah. And then there are further smaller corrections applied by the system constantly, accounting for things like the slight eccentricity of the orbits and even the rotation of the Earth, the Sagnac effect. It's all relativistic physics ensuring nanosecond accuracy.
So literally every time I use my phone's map, I'm relying on Einstein being right about space-time warping.
You absolutely are. It's maybe the most direct everyday consequence of relativity theory.
And the sources hinted these super precise clocks might do even more in the future.
Potentially, yes. They're becoming so sensitive that networks of connected atomic clocks might be able to detect tiny, tiny shifts in gravitational potential.
Which could mean
It could mean detecting the subtle bulging of the ground before a volcanic eruption, maybe, or measuring the loss of mass from melting ice sheets by the minuscule change in local gravity. Really precise geodesy.
amazing, from
Good.
finding your car to monitoring volcanoes. And yet, it still feels weird, doesn't it? One source mentioned that the whole idea can just feel senseless compared to our everyday intuition of time.
It really can. Our brains evolved in a world where relativistic effects are utterly negligible. Absolute time feels right. One perspective mentioned in the sources is, well, maybe time isn't changing. Maybe it's just the rate of physical processes that changes.
Like heartbeats or atomic vibrations just happen slower under certain conditions.
Right. Is it time itself or the things happening in time? But the sources clarify that the standard, incredibly successful model in physics is that space-time itself is relative, and the rate of time's passage changes.
Sticking to absolute time just doesn't seem to work with the observations, like the constant speed of light or GPS.
Exactly. Trying to reconcile everything from a single absolute time perspective seems impossible. Think about the observer falling into a black hole versus the distant observer watching. Their experiences of time are irreconcilably different, yet both are valid within their own reference frames. Relativity handles that. Absolute time struggles.
Even how we define the second, based on cesium atoms.
Implicitly needs context, as one source pointed out. A second based on which cesium atom, one at sea level, one on a mountain, one in a fast jet. To be truly precise, you have to specify the reference frame and gravitational potential. It underlines the relativity of time measurement itself.
Okay, so boiling it all down, time dilation is real, it's confirmed, it's fundamental.
Yep. Predicted by Einstein, verified by experiment, caused by differences in speed and gravity.
It affects everything, not just clocks. And it's not just abstract theory. It's essential for technology like GPS that we rely on constantly.
Absolutely. It fundamentally challenges that gut feeling we all have about time being this steady universal river flowing the same for everyone. It's just not.
Which leaves us with a pretty profound thought to chew on, doesn't it?
It really does.
If time flows differently all over the universe, depending on speed and gravity, what does now even mean on a cosmic scale? Is there such a thing as a universal now?
Or maybe think about it this way. This deeply theoretical, almost philosophical concept about the geometry of space-time. It's the bedrock of a technology that tells you exactly where you are on this planet. How does knowing that connection change how you see physics, or even just your phone's map app? Something to ponder.